Welcome to the Deep Dive. Today, we're tackling something you've probably wondered about. AI seems to be everywhere, right? Transforming everything. But how does it actually handle something as complex, as vital, as predicting the weather?
Especially when things get really wild. There's been a lot of buzz about AI weather models, how fast they are, how efficient.
Absolutely. But we're zeroing in on something, well, bit surprising today, based on a new study.
Exactly. We're digging into where AI, despite all its speed and general success, maybe, falters, specifically when facing those really extreme, record-breaking weather events, the ones that cause the most damage.
Right, that's our mission. We're looking at excerpts from this paper, Numerical Models Outperform AI Weather Forecasts of Record-Breaking Extremes by Zhanwei Zhang and colleagues.
Yeah, it's a fascinating piece.
We want to unpack what they found. How does AI stack up against traditional models when predicting these truly unprecedented events?
We'll explore the details, the insights, some are pretty eye-opening, and what it all means for, well, for you when you need a reliable forecast.
Okay, let's dive in. So first off, let's be clear. AI has made huge leaps in weather forecasting, no question.
Oh, definitely. Models like GraphCast, Pangu-Weather, Fuxi, they've been genuinely revolutionary in many ways.
They often outperform the standard physics-based models, the NWP systems, on lots of common benchmarks.
And they are incredibly fast. That speed plus the energy efficiency, that's a massive advantage.
But, and here's the pivot, the study asks a critical question. Okay, AI is great on various benchmark tasks, but how well can it actually extrapolate?
Right. Can it reliably forecast these truly unprecedented extreme events, things it hasn't really seen in its training data?
That's what this study was specifically designed to test, wasn't it? Focusing only on these record-breaking events.
Precisely. It's about testing that limitation, that out-of-distribution challenge.
So what exactly counts as record-breaking in this context? How do they define it?
It's quite rigorous. We're not just talking bad weather. These are events that are genuinely unprecedented in the historical observations. And it's defined locally, like for each specific grid point on the map, and even for a specific calendar month. So a record heat in July for London, for instance.
So really specific records.
Exactly. Think of things like the 2021 Pacific Northwest heat wave, completely off the charts, or the 2010 Russian heat wave, the 2003 European one.
Wow, those are major.
And major winter storms, too, like Lothar in '99 or Kirill in 2007. These are sometimes called black swan events or record-shattering.
Because they just blow past previous records?
Precisely. And crucially, the AI models they tested were trained on data from 1979 up to 2017.
Right.
Then they tested them specifically on record-breaking events that happened after that in 2018 and 2020, events that exceeded anything in that 1979-2017 training data.
Okay, so testing them on things they literally hadn't seen before.
Exactly. And that leads us straight to the first really big finding.
It is.
For these specific record-breaking conditions, extreme heat, extreme cold, extreme wind, the traditional numerical model, HRES from the ECMWF.
The European Center, yeah. Considered one of the best physics-based models.
Right. It consistently did better than the state-of-the-art AI models tested.
Consistently. That's surprising, given the hype around AI performance.
It is. It's a direct contrast to how well AI often performs on more, let's say, normal or moderately extreme weather.
So when it counts the most, the old ways are still holding up better. Let's get into the details. How much better?
Well, the forecast errors in the AI models were just consistently larger for these record events compared to HRES.
Across the board, like short-term, long-term forecasts.
Pretty much across all lead times. The gap was most noticeable in the shorter forecasts, say up to a few days out. But even beyond 5 days, HRES still generally performed better, though the difference wasn't quite as stark.
Okay, so the errors are bigger, but why? What's causing the AI models to struggle more?
This is really the crux of it. The research points clearly to AI models tending to systematically underestimate the intensity of these events.
Underestimate. So they see something extreme's coming, but they don't predict just how extreme it will be.
Exactly. For example, they predict record heat waves as being, well, less hot than they actually turn out to be. And they predict record cold snaps as being less cold.
So they're biased towards the middle, almost.
In a way, yes. The paper specifically shows this for GraphCast, and heat records a clear underprediction trend. It's not just random error, it's a systematic thing.
So I was thinking of an analogy, is like the AI sees a really tall building, it knows it's tall, but when a new record-breaking skyscraper goes up,
Yeah.
it just can't quite grasp how much taller it is. Like it has some kind of built-in limit.
That's actually a really good analogy. The study backs that up.
Yeah, so.
They found that the errors in the AI models grew almost linearly with how much the event exceeded the previous record.
Whoa, okay, so the more record-breaking the event.
The bigger the underestimation by the AI.
And HRES, the traditional model.
HRES showed a pretty much constant error level for temperature records, no matter how much they exceeded the previous record. For wind, there was a slight underestimation, but much, much less pronounced than with the AI models.
So HRES doesn't have that same problem with extrapolation.
Exactly. This systematic, one-sided bias in the AI models really suggests a fundamental issue with extrapolation, or what researchers call out-of-distribution generalization, forecasting things truly outside their learned experience.
Okay, this is fascinating. It's not just about predicting the intensity, though, is it? What about predicting if the event will even happen? Did the AI models even forecast the occurrence of these records?
That's another key finding, and frankly another challenge for the AI models in this study.
Uh-oh.
They systematically underpredicted the total number of record-breaking events compared to the actual observations, the ground truth data they used, called ERA5.
So they just missed them sometimes.
Yes.
Yeah.
Which results in a high number of what are called false negatives. They failed to predict a record event that actually happened, and that means they have low recall.
And HRS.
HRES, on the other hand, forecasted a number of records that was much more in line with the ground truth. It wasn't perfect, but much closer.
Wow. So if an AI model doesn't even flag that a potentially record-breaking heat wave or storm is on the horizon, that's a huge problem for warnings, for preparations.
Absolutely. The real-world impact could be massive. You need that heads up.
How did the study measure this specifically?
They use something called precision recall curves. It's a standard way to evaluate this kind of prediction. HRES was consistently closer to the ideal point, meaning high precision and high recall for heat, cold, and wind records.
And that contradicts some earlier work, doesn't it? I thought some studies suggested AI was actually better for extremes.
It does contradict some findings, yeah. Those earlier studies might have focused more on moderate extremes, perhaps, not these truly record-shattering events that push the boundaries of the historical data.
Interesting distinction.
And another really interesting, maybe slightly concerning detail. All the AI models they looked at tended to make mistakes on the same events.
Really? Why would that be?
Well, it suggests they might share similar biases, likely learned from the common training data, that ERA5 dataset from 1979-2017. They learned the same limitations, perhaps?
Okay, this all seems to point towards a really fundamental difference in how these models work. Can you break that down? Why this big gap when it comes to record breakers?
Yeah, this is the core of it, really. Current AI weather models are essentially data-driven. They use neural networks.
Learning patterns from the past.
Exactly. They learn complex patterns and relationships from the vast amounts of historical weather data they're trained on, in this case, 1979 to 2017. They get incredibly good at interpolating within the range of what they've seen.
Interpolating, meaning predicting things similar to what's happened before.
Right. But the big challenge is extrapolation. Predicting something fundamentally new, something that lies outside the boundaries of that historical data, that's where they seem to struggle.
And the traditional models, like HRES, how do they differ?
They operate on a completely different principle. HRES and similar NWP models are physics-based.
Meaning they use the laws of physics.
Precisely. They rely heavily on partial differential equations, basically. Complex mathematical formulas that describe how the atmosphere behaves based on our understanding of fluid dynamics, thermodynamics, etc.
So they simulate the atmosphere's physics directly.
Yes. And because they're grounded in these physical laws, they have an inherent capability to extrapolate. They aren't strictly bound by the range of events in the historical data in the same way an AI model is.
They don't have that implicit soft cap you mentioned earlier.
Exactly. They can, in theory, simulate conditions never observed before if the physics dictates it. Plus, another point the study mentions is that deterministic AI forecasts can sometimes smooth out very fine details.
Like sharp wind peaks.
Yeah, those very localized, intense features. And that smoothing can make it harder for them to capture the intensity of localized records. It's just a fundamentally different approach.
Okay, so given these limitations, especially for the most dangerous events, does this mean AI is, well, not the future for weather forecasting? Should we stick with the old ways?
Oh, definitely not. We shouldn't abandon AI at all. The study itself acknowledges how incredibly fast AI is evolving.
Right, this field moves quickly.
Very quickly. This isn't an indictment of AI in general, but rather a snapshot of current limitations for this specific, very challenging task. The paper actually points to several really promising ways forward.
Okay, good. So it's not all bad news for AI.
Yeah.
What are some of those solutions? How can AI get better at predicting these extremes?
There are a few key strategies being explored. One is called data augmentation.
Augmentation, adding more data.
Sort of, but smarter data. The idea is to train AI models not just on past observations, but also using output from numerical climate models.
Ah, so using simulations to create more extreme examples.
Exactly. Climate models can generate physically plausible, really extreme events that might not exist in our relatively short observational record. This can potentially expose the AI to a wider range of possibilities during training.
Has that shown promise?
Yes, actually. The paper mentions an example where training an AI model called ForecastNet on relevant climate model data improved its ability to predict tropical cyclones.
Okay, that makes sense. What else?
Another big area is hybrid modeling.
Hybrid. Mixing the two approaches.
Precisely. Combining the speed and efficiency of AI with the physical consistency and extrapolation power of the traditional models.
How would that work?
Well, you could potentially replace certain parts of a traditional physics-based model, maybe some complex calculations that are very computationally expensive with faster AI components if you can ensure the physics remain sound. It's about getting the best of both worlds.
Interesting. A blend.
And a third approach involves the AI's training process itself specifically, using specialized loss functions.
Loss functions, that's like the goal the AI is trying to achieve during training, right?
Yeah.
Minimizing errors.
Exactly. Right now, most AI weather models are trained to minimize errors across all weather conditions to get the best average forecast. But you could design loss functions that put more weight on getting the extreme events right, basically telling the AI, it's really important you don't miss these big ones, even if it makes your average performance slightly worse.
So prioritizing the prediction of extremes during the learning process itself.
Exactly. Teaching it specifically to pay more attention to the tails of the distribution, the rare but high-impact events.
This is all really fascinating. It feels like even as AI races ahead in so many areas, for something this critical, this fundamental, like predicting weather extremes that could devastate communities, those models, built on the underlying physics, still have a really crucial advantage right now. Their ability to extrapolate, to predict something genuinely new based on physical laws, that's incredibly valuable.
It is. It's a potent reminder that understanding the fundamental principles can be irreplaceable, especially when dealing with the unprecedented.
So it really leaves us with a big question, doesn't it?
Yeah.
Especially for you, the listener.
Absolutely. Think about this. We know record-breaking weather events are becoming more common because of climate change. We see the strengths of AI speed, efficiency, great performance on average, and we see the strength of traditional models that physical grounding, better extrapolation for the biggest extremes.
But they're slower, more computationally expensive.
Right. So the question is, how should we move forward? How do we build the best possible warning systems? Do we pour all our resources into making AI better at extrapolation, develop those hybrid models? Or should we focus on running both types of models in parallel, leveraging the strengths of each?
It's a complex balance.
It really is. How do you think we should best invest and integrate these powerful technologies to protect ourselves against future extremes? Prioritize refining AI, focus on the physics, or push for synergy? It's something weather services and researchers are grappling with right now.
We've certainly taken a deep dive today into the real complexities of weather forecasting. It's shown the incredible power, but also the surprising current limits of AI when pushed to the absolute edge. And it highlights the enduring value of those physics-based approaches for the events that matter most.
A lot to think about.
Indeed. Thank you for joining us on this deep dive.